In the volcanic sand of Iwo Jima, February 1945, Japanese artillery spotters watched through field glasses as American Seabees worked under fire. What confused them wasn't the bravery. They expected that from their enemy. What didn't make sense was the speed. The Americans were assembling buildings faster than the Japanese could destroy them. Steel panels appeared from nowhere, curved structures rising in hours where conventional barracks would take weeks. The spotters radioed coordinates, but by the time shells arrived, the structures stood complete, their arched profiles deflecting blast waves that shredded everything else on the beach. They weren't wrong to be puzzled. What they were witnessing was the culmination of an engineering revolution that began 1,200 miles away on a December morning that changed everything. December 7, 1941. Pearl Harbor burns, and within 72 hours, the United States military faces a logistics nightmare that has nothing to do with battleships or aircraft carriers. Across the Pacific Theater, from the Philippines to Wake Island, American forces are sleeping in canvas tents that disintegrate under tropical downpours within 3 weeks. The War Department's morning briefings turned grim when field reports arrived describing entire supply depots flooded, ammunition ruined, and soldiers hospitalized with pneumonia because their shelter literally fell apart during monsoon season. Traditional wooden barracks require skilled carpenters, weeks of construction time, and lumber that simply doesn't exist on remote coral atolls. The Navy calculates it would take 18 months to build conventional housing for the forces they need to deploy immediately. 18 months. The Japanese would own the Pacific by then. In Washington, Brigadier General Eugene Raybould stands before a crisis table covered in weather maps and construction timelines. His engineers present the impossible equation. They need structures that can be manufactured in Pennsylvania, shipped 10,000 miles through submarine-infested waters, assembled by exhausted Marines who've never held a wrench, and survive everything the Pacific can throw at them. 130-degree heat, Category 5 typhoons, monsoons that dump 15 inches of rain in 6 hours, and the very real possibility of Japanese bombing runs. The standard Army tent costs $12 but lasts 1 month in jungle conditions. A wooden barracks building costs $8,000 and requires a construction crew for 6 weeks. Neither option works when you're island hopping across the Pacific and need shelter for 50,000 men yesterday. The math is brutal. At conventional construction rates, the war would be over before half the troops had roofs. Soldiers are already writing letters home describing how they wake up with their boots full of rainwater, how fungus grows on their uniforms overnight, how the temporary tents collapse during storms and send men scrambling in the mud at 0300 hours. The Medical Corps reports that respiratory infections are hospitalizing more men than enemy action in some sectors. This isn't just about comfort. It's about maintaining a fighting force that doesn't rot away before seeing combat. The impossible requirements. The specifications that land on engineering desks across America in January 1942 sound like science fiction written by someone who's never actually built anything. Design a building that weighs less than a Jeep, fits on a single rail car, requires no foundation, assembles in 1 day with basic tools, costs less than $1,000, and survives conditions that destroy permanent buildings. Oh, and have 10,000 units ready to ship in 6 months. Most firms look at these requirements and politely decline. A few recognize the opportunity hiding inside the impossibility, because this isn't really a construction problem, it's a manufacturing problem disguised as architecture. And America in 1942 knows how to manufacture things. The British, who've been fighting longer, offer a clue wrapped in their own painful experience. Since 1916, they've used Nissen huts, semicircular steel shelters invented by Canadian engineer Peter Nissen during World War I. These corrugated iron half-cylinders house 30 soldiers, require no skilled labor to erect, and laugh at North African sandstorms. In the Libyan desert, where Lawrence of Arabia fought his war, Nissen huts provided the only reliable shelter for thousands of British troops, but the Nissen design has critical flaws for Pacific deployment. The British version uses heavy steel panels that need specialized lifting equipment to position. The ventilation system works for the Libyan desert but turns the interior into a steam cooker in Philippine humidity. Most damaging, each hut requires custom foundation work, concrete pads or wooden platforms, which brings you right back to the carpenter problem. Commander John Philip Drosfeld of the Navy's Bureau of Yards and Docks studies the Nissen specifications and sees both genius and fatal weaknesses. The genius: arch shape naturally deflects wind and sheds water without complex engineering. The problems: a laundry list that would doom the design in Pacific conditions. The British huts weigh 3 tons when disassembled. They use internal wooden frames that become feasts for termites in tropical climates. And those 2 small windows designed for Scottish weather? They'd turn these things into ovens at Guadalcanal's 98-degree average temperature. Drosfeld circles the ventilation specs in red ink and makes notes in the margins. The Nissen hut is a starting point, not a solution. Everything about it needs to be reimagined for an enemy more relentless than the Wehrmacht, the Pacific environment itself. But there's another voice in this conversation, and it comes from an unexpected corner of American intellectual life. Buckminster Fuller has been preaching about prefabricated housing since the 1920s, though most architects dismiss him as a crank with wild ideas and wilder hair. His Dymaxion house concept, factory-built, lightweight, assembled on site, reads like prophecy when you're facing global war. Fuller's published papers circulate through engineering departments, and his core insights prove invaluable even though the military never directly consults him. Treat buildings like manufactured products, not construction projects. Use industrial materials instead of traditional lumber. Design for rapid deployment using mass production techniques borrowed from automobile factories. In peacetime, these ideas sound radical. In wartime, they sound like survival. The Navy consolidates this thinking at their facility in Quonset Point, Rhode Island, a freshly commissioned air station on Narragansett Bay. The location isn't random. Rhode Island has deep manufacturing expertise in sheet metal from its jewelry and silverware industries, plus proximity to steel mills in Pennsylvania and shipyards that understand marine-grade corrosion resistance. More importantly, it's far enough from combat zones to work without interruption, but close enough to ports that prototypes can ship quickly. In March 1942, the Navy assembles an unusual team. Structural engineers from the Strandlund Steel Corporation who've been building prefab farm buildings. Architects from George A. Fuller Construction Company who specialize in rapid assembly methods. Navy officers who've actually served in the Pacific and know what typhoon-proof really means versus what it means on paper. And civilian consultants who understand that this problem requires thinking sideways, looking at grain silos, railroad cars, and water towers for inspiration, rather than traditional buildings. The team lead is Otto Brandenberger, a structural engineer whose previous claim to fame was designing economical farm buildings for Midwestern agriculture. His Strandlund steel barns use self-supporting arched panels. No internal frame needed, which means no wood for termites to eat and no complex joinery to fail during storms. Farmers from Iowa to Nebraska know his barns survive tornado season year after year, often the only structures left standing when winds reach 200 miles per hour. Brandenberger's radical proposal: eliminate the Nissen hut's wooden skeleton entirely and make the corrugated steel skin carry all the loads. This violates conventional architectural wisdom in 1942, where steel is for bridges and skyscrapers, not self-supporting buildings. But Brandenberger knows his barns have survived Midwest tornadoes without internal framing, and he's willing to bet the same principle scales up. The math says it should work. Physics doesn't care whether you're sheltering cattle or Marines. The British contribute another crucial element through their painful experience. Their Nissen huts in Burma and Singapore have taught them exactly how tropical environments destroy buildings, and they're willing to share every hard-learned lesson. Fungus isn't just cosmetic. It literally eats through wood preservatives and paint within months. Humidity doesn't just make things damp. It corrodes metal fasteners until roofs collapse. Insects aren't merely annoying. Carpenter ants can reduce wooden support beams to hollow shells in one season. The British reports read like horror stories. Entire supply depots collapsing, ammunition rendered useless by rust, medical supplies destroyed by mold. But they provide the Quonset team with a checklist of everything that must be engineered out of the design from day one. No wood in contact with ground. All steel hot dip galvanized, not just painted. Ventilation aggressive enough to prevent condensation. Every fastener accessible for replacement without disassembling the structure. By April 1942, the hybrid vision crystallizes. Take the Nissen hut's brilliant arch geometry. Strip out everything that makes it heavy or vulnerable. Add Fuller's mass production philosophy and American steel manufacturing muscle. Then engineer every detail for the specific hell of Pacific Island warfare. The result won't look like any building anyone has seen before. But that's fine. Beauty isn't the mission. Survival is. April 15th, 1942. Otto Brandenberger walks into a Quonset point warehouse with 30 engineers and a deadline that would be laughable if the war situation weren't so desperate. 60 days to design, prototype, test, and approve a completely new building system that doesn't yet exist. The Navy isn't asking for a concept study or preliminary drawings. They want finished specifications ready for mass production before summer. The team works in shifts around the clock, sleeping on cots pushed against the warehouse walls, subsisting on Navy mess hall coffee and the kind of pressure that either produces brilliance or complete collapse. There's no time for failure. While they're sketching and calculating, men are dying in the Pacific because they don't have adequate shelter. Brandenberger divides his crew into specialist teams. One group tackles aerodynamics and structural loading, figuring out how to make a curved steel tunnel survive hurricane-force winds. Another team figures out how to nest components for shipping, maximizing how many complete huts fit on a single cargo vessel. A third works exclusively on the joint and fastener problem that plagued the British design, because if the panels can't connect reliably in field conditions, nothing else matters. The first radical decision happens on day 3. Traditional architectural drawings take weeks to produce, and the team doesn't have weeks. Instead, they build in real time. Sketch a detail in the morning. Have the metalworking shop fabricate it by afternoon. Test it overnight. Revise by dawn. This iterative prototyping approach is standard in 2025, but revolutionary in 1942 when buildings are designed completely on paper before a single piece is cut. The warehouse floor becomes a laboratory scattered with failed joint experiments, bent test panels, and increasingly refined versions of each component. Engineers chalk calculations directly on the concrete floor. Machinists modify tools to cut specific profiles. Welders experiment with seam techniques that can be replicated in mass production. The team steals a technique from aircraft manufacturing. Every part gets a number, every revision gets documented, and nothing moves to the next prototype generation without solving the previous version's failure points. By week 2, the warehouse walls are covered in numbered drawings showing the evolution from concept to working design. Visitors compare it to watching biological evolution compressed into days instead of millennia. The dimensions come from brutal practicality rather than aesthetic choice. 16 feet wide, the maximum that fits on a standard rail car without special permits. 20 feet long per section, short enough that 4 men can lift a panel, but long enough to create usable interior space. 48 feet total length when assembled, housing capacity for 36 men with bunks, or converting to office space, medical stations, or supply storage. The Quonset team discovers that this size hits a sweet spot in structural engineering. Make it smaller and you waste shipping capacity. Make it larger and the panels become too heavy for field assembly, or the arch starts requiring internal supports that reintroduce all the problems they're trying to eliminate. The numbers aren't arbitrary. They're the result of testing dozens of configurations and finding the one that balances all the competing requirements. The arch radius calculation consumes 2 full weeks of the 60-day deadline. This single dimension, how much curve to give the roof, determines whether the structure survives or fails in the field. Too flat and wind forces could peel the structure like a sardine can. Too steep and you waste interior headroom and create difficult end-wall geometry that complicates manufacturing. Brandenberger's team settles on an 8-foot radius, a perfect semicircle that provides 7 feet of headroom at the sides and creates what structural engineers call a self-bracing arch. The corrugated steel naturally wants to hold this curve, which means the panels can be thinner and lighter than flat sheets would require for the same strength. It's elegant physics hiding inside practical geometry. They run load calculations showing this design can theoretically handle snow loads up to 40 pounds per square foot and wind speeds exceeding 100 miles per hour. But theoretical calculations and Pacific typhoons are different animals. The team knows the real test comes later, in conditions they can only imagine from weather reports and survivor accounts. The corrugations themselves add a second layer of brilliance. Those ridges running lengthwise create structural rigidity, the way folding a piece of paper makes it stronger than leaving it flat. Each corrugation acts like a tiny I-beam, resisting bending forces that would crumple smooth sheet metal. The specific profile, 2.67 inches on center, 0.75 inches deep, comes from testing dozens of variations. Too shallow and the panels lack stiffness. Too deep and they're difficult to manufacture and nest efficiently for shipping. What emerges is a structure where every element serves multiple purposes. The corrugations provide strength while allowing rainwater to shed quickly. The arch shape deflects wind while maximizing interior volume. The overlap pattern between panels creates weather-tight seals while allowing field assembly with basic hand tools. Nothing is wasted. Every design choice solves at least two problems simultaneously. By day 40, they have something that looks like it might work. A Frankenstein's monster of riveted panels, experimental joints, and borrowed hardware. The first complete prototype goes up on May 25, 1942, assembled by 6 sailors who've been given 4 hours of instruction and basic hand tools. The assembly time, 14 hours, which is encouraging but not yet good enough. The Navy wants single-day construction capability because marine landing schedules don't allow for multi-day building projects. You can't leave a partially assembled structure overnight when Japanese bombers make regular visits. The team identifies the bottleneck immediately, the floor system. They've been trying to include a wooden floor as part of the package, but it's the slowest part to assemble and the first thing to rot in tropical conditions anyway. The solution is elegant in its simplicity. Eliminate the floor entirely from the basic design. The hut sits directly on whatever surface exists: coral, sand, dirt, or, if you're lucky, gravel. For applications requiring finished floors, those can be added later as a separate project. But the basic shelter achieves weather protection without them. This single decision cuts assembly time to 8 hours and reduces shipping weight by 1,200 pounds per unit. On June 10, 1942, the final prototype stands complete. 96 corrugated steel panels, each weighing less than 50 pounds, bolt together to create 720 square feet of enclosed space. Total materials cost, $1,094. Total weight, 9,000 pounds, light enough to ship efficiently but heavy enough to stay anchored in storms. The complete kit fits on one standard flatbed railcar measuring 40 feet long. Brandenburger walks around the structure with a checklist, testing every joint, examining every panel connection, looking for failure points. The warehouse crew gathers in silence, watching their creation get judged. 2 months of 18-hour days have produced this curved steel tunnel. Now it needs to prove it can survive what's waiting in the Pacific. The prototype looks crude compared to traditional buildings, more industrial warehouse than military barracks. But Brandenburger sees something else. He sees democracy-made steel, a design so simple that any soldier can assemble it, so robust that nature can't easily destroy it, so economical that America can manufacture them by the thousands. Most importantly, he sees men surviving storms and bombs inside structures that didn't exist 60 days ago. The real test begins when the Quonset prototype faces the engineering equivalent of enhanced interrogation. Navy structural engineers arrive with wind load tables, typhoon data from meteorological stations across the Pacific, and healthy skepticism that this corrugated tunnel can survive what nature throws at tropical islands. The numbers they're working with aren't theoretical. They're pulled from actual weather events that killed people and destroyed infrastructure. Typhoon Gloria hit Guam in November 1940 with sustained winds of 140 miles per hour and gusts reaching 180. The 1935 Labor Day hurricane that killed 400 people in the Florida Keys produced winds so powerful they sandblasted paint-off buildings and drove wooden planks through palm trees like spears. The 1938 New England hurricane, still the most powerful storm to strike New England in recorded history, generated winds of 186 miles per hour and destroyed 4,500 buildings in Rhode Island alone. If Quonset huts fail in a storm, the result isn't just property damage. It's dead servicemen and destroyed equipment. The engineers need to know, really know, that these structures will protect the men inside them. Brandenburger's team starts with the fundamental physics of why the arch shape works. When wind hits a flat wall, it creates what engineers call a pressure coefficient. The wind pushes directly against the surface with maximum force, trying to punch through or tip the structure over. But a curved surface deflects wind upward and around, reducing that pressure dramatically. Think of how water flows around a river stone versus slamming into a dam wall. The semicircular Quonset profile means hurricane-force winds slide over the structure rather than trying to punch through it. Wind tunnel tests using scale models confirm the calculations. At 120 miles per hour, a flat wall experiences 45 pounds of pressure per square foot. The Quonset arch at the same wind speed experiences less than 20 pounds per square foot. The curve is literally fighting for you, using physics as armor. The corrugations add a second layer of defense. Those ridges running lengthwise create structural rigidity the way corrugated cardboard is stronger than flat cardboard. Each corrugation acts like a tiny I-beam, resisting bending forces that would crumple smooth sheet metal. Testing proves that corrugated panels can support 3 times more weight than smooth panels of the same thickness and material. The math gets fascinating when you examine how loads distribute through the arch. In a conventional rectangular building, the roof pushes down on walls. The walls push down on foundations, and everything depends on those vertical load paths staying intact. Storm winds can literally lift roofs off because they're separate elements just sitting on top of walls, held by nails or bolts that can fail. The Quonset arch changes this completely. It's a single continuous curve where every panel shares the load with its neighbors. Engineers call this a compression ring, and it's the same principle that keeps stone bridges standing for centuries without mortar. The hoop stress, the tension trying to spread the arch apart at its base, gets resolved by the ground itself. Each Quonset panel bolts to the adjacent panel with 3/4-inch steel bolts spaced every 6 inches, creating what's essentially a 48-foot-long steel cable wrapped in an arch shape. But theoretical strength means nothing without testing. The Navy sets up validation experiments that border on sadistic. They build a full-scale Quonset at Davisville, Rhode Island, and instrument it with strain gauges, pressure sensors, and deflection meters. Then they wait for the first major nor'easter. On March 3, 1943, a storm hits with 75-mile-per-hour winds and heavy snow loading, perfect test conditions. Engineers huddle in a nearby bunker, watching instruments and praying their calculations hold true. The structure flexes under the wind, bending in ways that would shatter a rigid building. But that's the genius of the design. It's supposed to flex. The arch breathes with the storm, absorbing energy rather than resisting it. The instruments record the structure flexing by less than 2 inches at the crown, then returning to its original shape when the wind subsides. The panel joints hold. Nothing leaks. The structure behaves exactly as the calculations predicted, which is both thrilling and slightly terrifying because it means they're about to bet thousands of lives on this design. The tropical environment testing proves more challenging than wind loads. You can't simulate years of jungle conditions in a Rhode Island warehouse. So the Navy ships a test unit to the Panama Canal zone, where humidity averages 85% year-round and temperatures stay above 80 degrees. If anything in the design is going to fail, the jungle will find it. 6 months later, the report comes back, and it's a mixed verdict. The galvanized steel panels show minimal corrosion. The zinc coating is doing its job, protecting the underlying steel from the constant moisture. The structural integrity remains intact, with no degradation in load-bearing capacity. But there's a serious problem with interior condensation. When hot, humid air hits the relatively cooler steel at night, water literally rains from the ceiling inside the hut. Sailors stationed in the test facility report waking up to puddles on their cots and equipment rusting from the constant moisture. The steel shell that protects them from external rain is creating internal rain through simple thermodynamics. The solution requires adding ventilation louvers at both ends and along the ridge line. Openings that let hot air escape and create airflow without compromising structural strength or weather protection. The design team experiments with different louver configurations, testing each version in environmental chambers that simulate Pacific conditions. Too few vents and the condensation continues. Too many and tropical rainstorms penetrate the interior. The final solution uses 8 louvered vents along the ridgeline plus large ventilator openings at each end wall. These vents add $47 to the unit cost but transform the hut from a steel sauna into something humans can actually occupy in tropical heat. The Navy accepts the cost increase without debate. What good is cheap shelter if soldiers die of heat stroke inside it? Testing also reveals problems with the original fastener specifications. Standard steel bolts rust through in saltwater environments within months, causing panel connections to fail. The solution? Every single fastener gets hot-dipped galvanized regardless of location or function. This adds another $28 to the unit cost, but field testing proves it's non-negotiable. Ungalvanized fasteners simply don't survive Pacific service. The foundation problem. The final engineering challenge is the foundation question. How do you anchor a 9,000-pound building to loose sand or coral without pouring concrete? The original Nissan hut design assumed solid ground and used concrete piers or wooden platforms. But Pacific Islands offer neither, just loose coral sand that shifts with every storm and tide. The answer comes from tent technology scaled up, steel stakes driven into the ground, connected to the hut's base with adjustable tension cables. For harder surfaces, the team designs a bolt pattern that lets the hut mount directly to wooden sleepers or pierced steel planking. The metal mats combat engineers lay down to create instant roadways across mud or sand. The beauty of this system is its forgiveness. The structure can flex slightly with ground movement without tearing itself apart. During earthquakes or storm surge, a rigid foundation would crack. The cable-anchored Quonset rides out the movement like a ship on rough seas, bouncing but not breaking. Engineers test this by building a Quonset on a platform designed to simulate earthquake motion. They shake the platform violently enough to knock a man off his feet while instruments measure the structure's response. The hut sways several inches at the peak but returns to center when the shaking stops. The panel connections hold. The base cables stretch and recover without permanent deformation. One engineer, watching the test, compares it to the difference between an oak tree and a palm tree in a hurricane. The oak resists the wind with rigid strength and sometimes snaps. The palm bends almost horizontal and survives. The Quonset hut is a palm tree made of steel. June 1942. The War Production Board approves Quonset hut manufacturing, and what happens next is American industrial capacity operating at its absolute peak. The Navy contracts with 10 major steel fabricators across the Midwest and Northeast, companies that were making grain silos and water tanks 6 months ago and are now retooling for military shelter production. The conversion happens with stunning speed. Factory floors are redesigned. New tooling is machined. Workers are retrained. Within 8 weeks, the first production units roll off assembly lines. The Strandlund Steel Corporation converts its entire Penrose facility outside Philadelphia to exclusive Quonset production. George A. Fuller Construction takes over a former automobile parts plant in Chicago. Great Lakes Steel dedicates 2 rolling mills to nothing but corrugated panel production. Smaller manufacturers across the industrial heartland add capacity wherever they have metalworking equipment. By August, these factories are collectively producing 1,500 complete huts per week, and the number keeps climbing. Production managers who spent the 1930s idled by the Depression now run 3 shifts around the clock. The same workers who built luxury cars and household appliances are turning out war shelters with automotive precision. The manufacturing process borrows heavily from assembly line logic. Massive steel coils arrive by rail, each coil 4 feet wide and containing enough steel for 30 panels. Rolling machines corrugate the flat steel, creating those structural ridges at precisely 2.67 inches on center. The corrugating process work hardens the steel, making it 30% stronger than the flat sheet that went in, an unexpected bonus that the engineers happily accept. Next, the panels go through galvanizing tanks where they're dipped in molten zinc at 850 degrees Fahrenheit. This isn't painting. It's a metallurgical bond where zinc atoms actually merge with steel atoms at the surface. The zinc coating sacrifices itself to corrosion before the underlying steel can rust. In Pacific saltwater air, this galvanizing means the difference between a 5-year lifespan and a 50-year lifespan. The process costs an extra $112 per hut, but proves non-negotiable after field reports show ungalvanized steel corroding through in 8 months. The Navy pays the premium without complaint. Spending $112 now beats rebuilding entire bases every year. Each complete hut kit gets packaged with obsessive attention to shipping logistics. The 96 corrugated panels nest inside each other like stacked bowls, reducing the package height from 8 feet to just 14 inches. Think about that transformation. A building 8 feet tall compresses to barely over 1 foot for shipping. It's architectural origami driven by desperate efficiency. The end walls, plywood sheets with pre-cut door and window openings, pack flat between the steel panels. All fasteners, bolts, and hardware get boxed in a single wooden crate that includes illustrated assembly instructions designed for men who might not read English fluently. The manual uses pictures and diagrams with minimal text, assuming the assemblers are exhausted Marines on a combat beach, not skilled construction workers with union cards. The entire kit loads onto one standard flatbed rail car measuring 40 feet long. This packaging density is crucial because every train heading to West Coast ports is carrying either Quonset huts, ammunition, food, or vehicles. There's zero room for inefficient cargo. The war effort moves on precisely calculated logistics, and the Quonset hut fits those calculations perfectly. The shipping choreography gets wild. Trains leave Philadelphia and Chicago daily, arriving at San Francisco, San Diego, and Seattle, where Liberty ships and specialized cargo vessels wait at dock. Longshoremen load complete huts into ship holds using the same crane systems designed for tanks and artillery. Each hut weighs only 9,000 pounds, less than many military vehicles, which means forklifts can handle them instead of requiring heavy cranes. A single Liberty ship can carry 200 Quonset huts plus their assembly hardware, representing shelter for 7,200 men. The War Shipping Administration tracks every cargo manifest because these aren't just buildings, they're strategic assets. A hut that ships to Guadalcanal in September might house a bomber crew by October, making the difference between operational aircraft and pilots sleeping in mud. The Pacific crossing takes 18 to 30 days, depending on routing and whether convoys have to dodge submarines. Ships traveling alone move faster but risk torpedo attack. Convoy sailing offers protection but adds days to the journey. The Navy accepts both risks because the alternative, not having shelter at all, is worse. At destination ports, Seabees, the Navy's construction battalions, wait to receive the shipments and move them forward to island bases. The Seabees are themselves one of the war's great improvisations, formed in 1942 specifically because the Navy realized it needed construction experts who could also fight. Their motto, "We build, we fight," captures the hybrid nature of their mission. Unloading a Liberty ship carrying 200 Quonset huts takes a full day of coordinated labor. Cranes lift the palletized loads from holds. Forklifts move them to staging areas. Cargo handlers check off inventory against manifests while officers decide which huts go to which forward bases. The entire operation runs with dock worker efficiency because any delay costs lives downrange. The really remarkable thing is how quickly the system scales. In August 1942, the Navy ships 2,000 huts to the Pacific. By December, that number reaches 8,000 per month. By mid-1943, monthly production hits 10,000 units. The logistics network moves so efficiently that huts ordered in Pennsylvania reach New Guinea within 40 days, including ocean crossing and trans-Pacific transport. That's faster than domestic mail delivery to some rural American addresses. The cost accounting tells the victory story. Each Quonset hut provides 36 men with weatherproof shelter for $1,094 in materials and approximately 60 man-hours of assembly labor. Compare this to conventional barracks: $12,000 in materials, 400 man-hours of skilled carpentry, and 6 weeks of construction time. The Quonset delivers shelter at 1/10 the cost and 1/20 the time. By mid-1944, the U.S. military has deployed over 160,000 units to every combat theater. That's housing capacity for nearly 6 million personnel, built in less than 2 years. To put that in perspective, it's equivalent to building a city the size of Philadelphia entirely from prefabricated structures while simultaneously fighting a global war. Guadalcanal, August 1942. The first combat-deployed Quonset huts arrive on a beach where the temperature hovers at 95 degrees with 90% humidity, and Japanese bombers make daily visits to crater anything that looks like American infrastructure. Marine engineers unload the flat-packed steel panels under sporadic artillery fire and start bolting them together in a coconut grove still showing scorch marks from the previous week's shelling. The assembly crews work stripped to the waist in the tropical heat, sweat pouring off them as they wrestle 50-pound panels into place. They're racing against time. Darkness brings Japanese air raids, and anything incomplete becomes a target. Within 12 hours, Henderson Field has 10 new structures housing maintenance crews for the battered F-4F Wildcats operating from the airstrip. The planes are America's only defense against Japanese attacks, and the maintenance crews need to work around the clock to keep them flying. The Quonset huts give them that capability, shelter that's not luxurious, but adequate, protected workspace where tools don't rust and parts don't get ruined by rain. The real test comes 3 days later when a Japanese bombing run scores a near miss. A 500-pound bomb detonates 40 yards from a hut full of aviation mechanics. The blast wave flattens surrounding palm trees. Trees that have stood for decades reduced to splinters in milliseconds. Canvas tents within 100 yards shred like tissue paper. Wooden structures collapse from the overpressure. The Quonset flexes. Dirt and shrapnel rattle off the corrugated steel like hail on a tin roof. The curved surface deflects the blast wave upward and around, just as the engineers predicted. When the smoke clears, the structure stands intact. Inside, 18 men sprawl on the floor, where the blast knocked them down, ears ringing, hearts pounding, but alive. Every single one walks out on his own feet. Word spreads fast through military channels. The new huts can take it. They're not indestructible, nothing is, but they're tougher than anything else America is putting in the field. Commanders start requesting Quonsets by the hundreds. The jungle environment proves as hostile as enemy action, just slower and more insidious. Within 2 weeks, red rust streaks appear on any ungalvanized fasteners. The salt air eats through standard hardware like acid, a combination of moisture, salt, and tropical heat that corrodes metal faster than anyone predicted. Fungus grows on everything that holds moisture, turning the inside surfaces into abstract art exhibits of black and green mold. Men wake up to find their uniforms spotted with mildew. Leather boots turn green overnight. Paper documents become useless pulp within days unless stored in sealed containers. The ventilation louvers that seemed adequate in Rhode Island testing barely move the suffocating air. Inside the steel shells, temperatures climb to 120 degrees during the day. Men compare it to working inside an oven. The metal becomes too hot to touch with bare hands. You need gloves just to adjust a door latch. Marines start propping doors open 24/7 and cutting additional vent holes with tin snips, violating structural specifications but making the huts livable. Some crews take matters further, cutting entire sections out of the side walls to increase airflow. Engineers back at Quonset Point hear about these field modifications with mixed feelings. The structures are supposed to be used as designed, but desperate men make desperate choices. These field modifications get documented in after-action reports and sent back to Quonset Point, where engineers incorporate them into later production runs. More ventilation, larger louvers, every single fastener galvanized regardless of location. The design evolves based on combat feedback in near real time, a remarkable feat of institutional learning during wartime chaos. Some forward-thinking supply officers start shipping paint specifically formulated for metal surfaces in tropical conditions. Crews discover that painting the exterior white or light gray instead of leaving it bare, steel reduces interior temperatures by 15 to 20 degrees, enough to make the difference between habitable and hellish. By 1943, standard procedure includes painting all Quonset huts white in tropical deployments. The Aleutian Islands campaign tests the design from the opposite extreme. Dutch Harbor and Adak see Quonset huts deployed where temperatures plunge to -40 and winds regularly exceed 100 miles per hour. The Japanese are fighting for these godforsaken rocks because they provide potential stepping stones to the American mainland. The weather makes combat almost secondary. Just surviving the environment becomes the primary challenge. The cold makes the steel brittle, and early units suffer from panels cracking at the bolt holes. Metal that's flexible in warm climates becomes glass-hard in sub-zero temperatures. When stressed by wind or snow loads, it fractures instead of bending. Engineers respond by specifying cold-rolled steel with different metallurgy for Arctic deployments. steel alloys designed to remain ductile at extreme temperatures. They also add rubber gaskets at every joint to maintain flexibility. The gaskets absorb movement without transmitting stress to the brittle metal. It's a simple modification that solves a potentially catastrophic problem. Heating the huts creates its own challenges. Warm air meeting frozen steel produces condensation that literally rains inside until crews learn to install insulation blankets and run ventilation even in sub-zero weather. The physics is counterintuitive. You need air circulation when it's 40 below outside, but the alternative is having water freeze on interior surfaces and create ice buildup that makes the structure uninhabitable. By winter 1943, weatherized Quonset models include internal insulation batting, double wall construction for extreme cold zones, and modified ventilation systems that prevent heat loss while managing moisture. Some models even incorporate vestibule entrances, small enclosed spaces before the main door that prevent heat loss every time someone enters or exits. The Arctic models cost nearly double the standard tropical versions, but they work. Men stationed in the Aleutians report that Quonset huts are the only structures that remain reliably habitable through winter. Traditional wooden buildings need constant maintenance to prevent frost damage. Canvas shelters are death traps. The Quonsets just sit there, ugly and functional, keeping men alive through 8-month winters where darkness lasts 19 hours a day. Palermo, Sicily, summer 1943. A Quonset hut pressed into service as an ammunition depot takes a direct hit from a German 88mm artillery shell. The shell, a high-velocity armor-piercing round designed to knock out tanks, penetrates the steel skin and detonates inside among crates of small arms ammunition. The resulting explosion should theoretically vaporize the structure. 20,000 rounds of .30-06 ammunition cooking off simultaneously produces an overpressure event that levels everything within 50 feet of conventional buildings. EOD teams approaching the wreckage expect to find nothing but a crater. Instead, the arched shape channels the blast force outward through the walls and roof in a pattern that leaves the structural frame twisted but standing. The explosion blows out both end walls and peels back several roof panels, but the basic arch remains intact. The compression ring principle means even catastrophic damage doesn't trigger total structural failure. EOD crews examining the wreckage note that a rectangular building would have collapsed completely, trapping anyone nearby under tons of rubble. The Quonset's inherent strength, that arch geometry that makes it resistant to external forces, also makes it surprisingly resistant to internal explosions. The force follows the curve outward, rather than bringing the structure down on itself. This incident gets written up and circulated through ordnance safety channels. Within months, ammunition storage protocols specify Quonset huts over wooden structures specifically because they're more likely to contain blast damage to the immediate area rather than creating catastrophic failures that spread destruction. The Pacific typhoon season of 1944 delivers the ultimate stress test. Super Typhoon Cobra hits the Philippines in December, with winds measured at 140 miles per hour and 20-foot storm surge. The storm is so powerful that it sinks 3 U.S. Navy destroyers, warships designed to survive heavy seas, by rolling them until they capsize. At Tacloban, the storm destroys 80% of all structures on the base. Wooden buildings explode into splinters as if hit by artillery. Concrete block structures collapse when wind undermines their foundations. Metal Quonset huts that aren't properly anchored roll across the landscape like enormous tumbleweeds, coming to rest hundreds of yards from their original positions. But of 43 Quonset huts on the base that were properly anchored, 39 survive intact. 4 suffer repairable damage, bent panels, torn seams, but no total failures. The survival rate is remarkable. 90% of properly installed Quonsets survive conditions that destroyed virtually everything else. Engineers analyzing the survivors find that proper anchoring matters more than any other factor. Huts with adequate ground attachment, either concrete deadmen, driven piles, or properly tensioned cable systems, ride out the storm. Those with improvised or insufficient anchoring fail, not because the structure can't handle the wind, but because inadequate foundations let the entire building move. The lesson is clear and gets incorporated into field manuals immediately. Spend the extra time getting the anchoring right. An additional 4 hours of foundation work can mean the difference between a structure that survives and one that becomes a tornado of steel panels, killing anyone in its path. The storm also reveals another important design feature. Because Quonset huts don't have windows in the curved sections, all the openings are in the flat end walls. They don't suffer from the window blowout problem that destroys so many conventional buildings. In hurricanes and typhoons, once windows break, wind enters the structure and creates internal pressure that blows the roof off from inside. Quonsets don't have this vulnerability. By war's end, field performance data from 50 combat zones feeds back into continuous design improvement. The 1945 production models bear little resemblance to the 1942 prototypes, even though the basic geometry remains identical. Better ventilation solves the tropical heat problem. Stronger fasteners eliminate the corrosion failures. Improved insulation options make cold weather deployment practical. Field-tested modifications transform a good design into an exceptional one. May 8, 1945. Victory in Europe. August 15, 1945. Victory over Japan. Suddenly, the United States military owns roughly 170,000 Quonset huts, scattered across 6 continents, and has absolutely no idea what to do with them. The original plan assumed these were temporary wartime expedients that would be scrapped or abandoned once permanent facilities could be built. They were supposed to last 2 years, maybe 3 if you were lucky. Nobody expected them to outlive the war, and certainly nobody planned for what happens when you suddenly have 170,000 perfectly functional buildings that nobody needs anymore. At hundreds of military bases slated for closure or downsizing, commanders look at their Quonset huts and see not obsolete wartime relics, but perfectly functional buildings that cost nothing to maintain and can be repurposed for virtually anything: storage, workshops, offices, recreation facilities. The huts just sit there, ugly and utilitarian, waiting for someone to find a use for them. The War Assets Administration, tasked with liquidating surplus military property, finds itself facing an unusual problem. There's more demand for used Quonset huts than they have inventory to sell. The civilian economy is exploding with pent-up demand after 4 years of wartime restrictions, but there's a critical shortage of everything needed for peacetime growth: buildings, housing, commercial space. The Quonset hut, designed for war, becomes an accidental solution to peace. The housing crisis comes home. Veterans returning home discover a housing shortage so severe that families are living in converted chicken coops, cars, and shared apartments with 3 other families. The construction industry, starved of materials and labor during 4 years of war, can't build fast enough to meet demand. Skilled carpenters are scarce. Lumber is expensive. Building codes designed for traditional construction make conventional buildings slow and costly. Into this crisis steps the Quonset hut, now available for civilian purchase at liquidation prices: $1,000 to $2,500 for a complete structure that would cost $8,000 to build conventionally, if you could even find contractors available to build it. For returning GIs desperate for their own space, the math is simple. They can buy a Quonset hut now or wait 2 years for a conventional house they probably can't afford anyway. The federal government actively encourages this repurposing through programs that prioritize veterans for Quonset purchases. Under the GI Bill, veterans can get loans to buy surplus military equipment, including housing. Suddenly, owning a home isn't a distant dream requiring decades of saving. It's an achievable goal with a war surplus structure and a small loan. By late 1946, suburban developments made entirely of Quonset huts spring up around every major city. These aren't scattered individual structures. They're entire planned communities designed around the unique characteristics of the military huts. Roger Young Village in Los Angeles houses 750 families in converted military huts. The development takes over 500 acres of former military land and transforms it into a community with streets, utilities, schools, and all the infrastructure of a normal neighborhood. The only difference is that every house is a curved steel tunnel. Vetville developments appear near universities where the GI Bill is flooding campuses with students who need immediate housing. At UCLA, Purdue, University of Wisconsin, and dozens of other schools, married student housing consists entirely of Quonset huts. Young couples starting families live in these structures, while husbands attend classes on veterans' benefits. The huts that sheltered men during war now shelter them during the transformation to peacetime life. The architectural adaptation gets creative fast. Families add wooden facades to the curved ends, making the structures look less like military surplus and more like quirky cottages. Interior walls divide the open space into bedrooms, living areas, and kitchens. Windows get cut into the steel sides, violating every structural principle but making the spaces actually livable for family life. Some owners go further, burying the entire structure halfway into the ground for earth-sheltered insulation. Others connect multiple huts end-to-end to create sprawling compound homes. A few ambitious souls stack 2 huts vertically, creating 2-story structures that look nothing like their military origins. Housing inspectors and building code officials initially balk at approving these modifications. The structures weren't designed for residential use. They lack proper insulation, plumbing connections, electrical systems designed for household use. But the housing shortage is so desperate that municipalities reluctantly grant permits. The alternative, homeless veterans, is politically and morally unacceptable. In Portland, Oregon, an entire neighborhood called Fairview Addition consists of 350 Quonset homes. Residents plant gardens, paint their steel walls cheerful colors, and build conventional-looking porches that disguise the utilitarian origins. From the street, if you squint, it almost looks like a normal suburban development. But the curved roof lines give it away. This is a neighborhood built from war surplus. The communities develop their own character. Everyone knows everyone else because they're all in the same situation. Veterans starting over, young families building lives, people united by the shared experience of living in converted military structures. The Quonset huts become symbols of something uniquely American: improvisation, practicality, and the determination to build better lives from whatever materials are available. Churches discover Quonset huts solve a different problem entirely, providing worship space for exploding suburban populations without the decade-long capital campaigns traditional church buildings require. In 1945, American suburbs are growing faster than anyone predicted. New housing developments spring up literally overnight, and families moving into these new neighborhoods need community institutions, schools, stores, and churches. Traditional church construction costs $150,000 to $300,000 and takes years of planning and fundraising. Young congregations can't wait that long. First Presbyterian Church of Levittown, Pennsylvania, the archetypal post-war suburb, holds services in a Quonset hut from 1952 until 1967, when they finally raise funds for a conventional sanctuary. Every Sunday, 200 people file into a curved steel tunnel for worship. The acoustics are terrible. Voices echo off the metal surfaces, making everything sound tinny. The aesthetics are underwhelming. No soaring Gothic arches or beautiful stained glass. But people can gather for worship next month instead of next decade. Dozens of congregations make the same calculation. $2,500 for immediate space beats, $150,000 for eventual grandeur. Methodist churches, Baptist churches, Catholic parishes, Jewish synagogues, religious communities of every denomination embrace the Quonset solution. Some paint biblical scenes on the interior walls to make the space feel more sacred. Others hang fabric from the ceiling to improve acoustics and soften the industrial appearance. The temporary church huts remain in service for 20, 30, even 40 years in some cases, outlasting the generations who first considered them stopgap solutions. When congregations finally build conventional sanctuaries, some keep the old Quonset huts for fellowship halls, Sunday school classrooms, or storage. The structures that housed prayers and baptisms and weddings and funerals become too emotionally significant to simply demolish. Education sees similar adoption. Post-war school enrollment explodes as the baby boom hits, and school districts face the same impossible math that plagued the military in 1942. They need classrooms immediately, and conventionally built schools take years to construct. Rural districts especially embrace Quonset classrooms. A single hut provides space for 30 students at 1/10 the cost of traditional construction. By 1950, an estimated 3,000 schools across the United States include at least one Quonset hut classroom. Some students spend their entire elementary education in these steel tunnels, learning multiplication tables and history lessons under curved ceilings that once sheltered B-29 crews in the Pacific. Teachers adapt to the unique challenges. The acoustics make classroom management interesting. Every sound echoes. The lack of windows in the curved sections means artificial lighting runs constantly. Temperature control ranges from freezing in winter to sweltering in hot weather, despite insulation efforts. But the classrooms work. Children learn, teachers teach. Educational outcomes in Quonset classrooms match or exceed those in conventional buildings because the structure doesn't determine the quality of education, the teachers do. The huts simply provide affordable space where learning can happen. Some of these classroom buildings remain in use into the 1980s and beyond, long past their expected lifespan. Maintenance crews paint them every few years and patch any rust spots, and the structures just keep serving. When schools finally demolish them to build modern facilities, longtime residents often protest. The old Quonset huts have become landmarks, part of the community's identity. The commercial sector joins the party with enthusiasm. Small businesses, machine shops, auto repair garages, warehouses, farm equipment storage recognize that Quonset huts deliver clear span space without internal support columns, making them perfect for industrial work. A welder can set up shop in a surplus hut for less than 2 months' rent in conventional commercial space. The open interior means you can move large equipment in and out easily. The steel construction means you can weld, cut, grind, and do all the things that make conventional landlords nervous. The structures are practically indestructible, so normal industrial abuse doesn't matter. Small manufacturing firms buy Quonsets by the dozen to expand production capacity. The post-war economy is booming, and companies need space to manufacture all the consumer goods Americans are desperate to buy after years of wartime austerity. Rather than wait for conventional buildings, manufacturers buy surplus Quonsets and start production immediately. Agricultural use proves especially popular. The original Strandlund Steel Corporation, having helped design military Quonsets, returns to manufacturing civilian versions specifically marketed to farmers. The sales pitch practically writes itself. Remember our steel barn designs? Well, we helped win the war with the same principles, and now you can buy war-proven structures for your farm. Thousands of Midwestern farms add Quonset storage buildings for grain, equipment, and livestock shelter. The maintenance requirements are minimal. Hose off the exterior once a year, check the bolts occasionally, and the structure lasts indefinitely. Farmers appreciate practicality over aesthetics. Who cares what it looks like if it keeps the tractor dry and the grain protected? By 1955, Quonset-style buildings, either genuine war surplus or new manufacture using the same design, dot the American landscape from coast to coast. They've become part of the visual vocabulary of mid-century America, as common as grain silos and water towers in rural areas, as familiar as warehouses in industrial zones. This civilian adoption creates an accidental architectural legacy that nobody predicted. Quonset huts become embedded in American visual culture as symbols of practicality over pretense, function over form, and make-do ingenuity. They appear in movies, television shows, and photographs as shorthand for post-war optimism mixed with austerity. Architectural historians initially dismissed them as temporary eyesores, not real architecture, as one critic sniffs in 1952. But by the 1990s, preservationists start recognizing surviving Quonset huts as important examples of adaptive reuse and vernacular architecture. Several achieve historic landmark status, protected as representing a unique moment when military technology successfully transitioned to civilian life. The National Park Service now maintains several preserved Quonset huts as examples of World War II-era construction. The structures that were too crude and utilitarian to be considered architecture in 1945 are now protected historical resources in 2025. Proof that time changes perspective on what matters in the built environment. Veterans who lived in Quonset communities develop fierce nostalgia for the structures. Reunion groups form, dedicated to preserving the memory of these transitional homes. Online forums share photographs and stories. Some families keep pieces of their original Quonset huts, a panel section mounted on a wall, a door used as a shed, physical reminders of where they started their post-war lives. The huts become metaphors for the greatest generation itself, tough, practical, unassuming, built to survive rather than impress. Whether that metaphor is accurate is debatable, but it's powerful. The Quonset hut stands for something larger than its corrugated steel and bolted panels. It represents a moment when America took tools designed for war and transformed them into instruments of peace. Modern disaster zones tell you everything about why the Quonset hut's DNA keeps reappearing in 21st century emergency response. When the 2010 Haiti earthquake destroys Port-au-Prince, relief organizations face the same equation American military planners confronted in 1942: immediate shelter for hundreds of thousands of displaced people, no existing infrastructure, no time for conventional construction, and conditions that destroy inadequate temporary housing within months. The solution that emerges borrows directly from Quonset principles, even when designers don't realize they're channeling 1940s military engineering. Arched steel frames, corrugated metal panels, prefabricated components that ship flat and assemble quickly. The basic formula hasn't changed because the underlying physics and logistics haven't changed. The United Nations High Commissioner for Refugees currently uses shelter systems called RHUS, refugee housing units, that are essentially Quonset huts with 80 years of material science improvements. Instead of corrugated steel, they use insulated composite panels. Instead of bolt-together assembly, they employ snap-fit connections, but the core concept remains identical: curved profile for structural efficiency and wind resistance, self-supporting arch eliminating internal framing, flat-pack shipping allowing massive quantities to reach remote locations, and assembly by unskilled labor with minimal tools. A two-person crew can erect a modern RHU in 4 hours, almost exactly matching the 1942 Quonset specifications. These units currently house over 200,000 displaced persons in refugee camps across Africa, the Middle East, and Asia. The structures protecting Syrian refugees in Jordan, Rohingya refugees in Bangladesh, and displaced persons in South Sudan are direct descendants of the structures Otto Brandenburger designed in Rhode Island. Hurricane-resistant construction has rediscovered arch geometry after decades of building conventional rectangular structures that hurricanes repeatedly destroy. After Hurricane Katrina devastated the Gulf Coast in 2005, engineers studying which buildings survived found that curved structures consistently outperformed rectangular ones. The Mississippi coast saw entire neighborhoods of conventional homes reduced to foundation slabs, while a handful of Quonset-style metal buildings stood intact with minor damage. Wind speeds exceeded 150 miles per hour, storm surge topped 20 feet. Traditional construction simply disintegrated. But the curved buildings survived. This empirical evidence triggered research into what structural engineers call aerodynamic architecture, designing buildings that work with wind forces rather than resisting them through brute strength. The result looks remarkably like a Quonset hut because the physics haven't changed since 1942. Wind flowing over a curve creates less pressure than wind slamming into a flat surface. Today, exactly as it did 83 years ago, building codes in hurricane-prone regions now include provisions specifically for arched structures, recognizing their superior wind resistance. Some municipalities actually incentivize arch construction through lower insurance rates and expedited permitting. The Quonset principle, work with nature instead of against it, has moved from wartime expedient to best practice. The modern tiny house movement unknowingly reinvents Quonset principles when designers seek maximum interior space with minimum materials and cost. Several companies now manufacture arch-roofed prefab cabins using the same corrugated metal and self-supporting curve that Brandenburger pioneered. These sell to buyers seeking affordable housing, disaster-resilient structures, or off-grid living solutions. The marketing emphasizes sustainability and modern design, rarely mentioning that the fundamental architecture is a World War II military shelter. The structures cost $30,000 to $60,000 for a complete living space, expensive compared to 1946 surplus huts, but cheap compared to conventional construction. Some high-end architectural firms have rehabilitated the aesthetic entirely, designing luxury versions with floor-to-ceiling glass end walls and premium finishes that cost $300 per square foot while maintaining the signature curved profile. The arch has gone from utilitarian necessity to design statement. What was ugly in 1942 becomes trendy in 2025, proof that aesthetic judgments change with time and context. Architecture schools now teach the Quonset hut as an example of successful design that prioritizes function over form. The structures appear in textbooks alongside Buckminster Fuller's geodesic domes and other experiments in efficient shelter. Students study the engineering principles and marvel at how a team of 30 engineers working under wartime pressure created something that still influences design 8 decades later. Perhaps the ultimate validation comes from space exploration, where NASA and private space companies designing Mars habitats keep arriving at Quonset-like solutions. Proposed Martian shelters feature arched profiles to resist the planet's severe dust storms, prefabricated components that ship on spacecraft, and self-supporting structures that don't require extensive foundation work in Martian regolith. The constraints of interplanetary construction, extreme environments, minimal tools, unskilled assembly, maximum strength from minimum materials, mirror the Pacific Theater challenges of 1942 so precisely that engineers independently rediscover the same solutions. When SpaceX proposes inflatable habitats that deploy from compressed packages and harden into arched domes, they're following the same logic that drove Quonset development. Minimize shipping volume, maximize deployed space, optimize for harsh conditions. NASA's plans for lunar bases include structures that look like Quonsets covered in regolith for radiation shielding. The 3D printed habitats that various companies propose for Mars generally feature curved profiles because curves distribute stress better than corners, the same principle that makes Quonset huts survive typhoons. When humans finally build permanent shelters on another planet, there's a reasonable chance those structures will owe their design heritage to 30 engineers working in a Rhode Island warehouse during the darkest days of World War II, solving an impossible problem with corrugated steel and brilliant simplicity. Today, Quonset huts still serve in surprising places. Thousands remain on active military bases, having outlived multiple generations of soldiers. Some have been in continuous use for 80 years, hosting everything from storage to offices to recreation facilities. The structures that were supposed to last 5 years have persisted for more than 16 times their intended lifespan. Antarctic research stations use Quonset-style buildings because they handle extreme conditions better than conventional construction. The South Pole's Amundsen Scott Station includes several arched structures descended directly from the World War II design. When you're operating in an environment that makes the Arctic look hospitable, you need shelter that works regardless of conditions. Industrial facilities worldwide still deploy Quonset-style buildings for temporary and permanent purposes. Mining operations in remote locations use them because they can be helicoptered in pieces to sites where conventional construction is impossible. Oil and gas operations in harsh climates rely on them for worker housing and equipment protection. Museums have collected and preserved several World War II-era Quonset huts as historical artifacts. The National World War II Museum in New Orleans maintains a complete original unit with authentic interior fittings. Visitors walk through and experience what millions of servicemen experienced: the curved walls, the echoing acoustics, the sense of being inside a steel tunnel. It's living history, preserved in corrugated metal. Private collectors restore vintage Quonset huts as workshops, studios, or unique living spaces. These preservation efforts keep authentic examples in existence while allowing modern use. Some owners paint elaborate murals on the interiors, transforming utilitarian war surplus into artistic statements. The huts that were designed for pure function become canvases for self-expression. The enduring principles. What makes the Quonset hut remarkable isn't just that it solved an immediate wartime problem. It's that the solution remains relevant 83 years later because it addresses fundamental challenges that don't change: how to provide shelter quickly, cheaply, and reliably in difficult conditions. The principles that drove the design in 1942 still matter in 2025, and they are as follows. Simplicity: complex systems fail in unpredictable ways. Simple systems fail, obviously, or don't fail at all. The Quonset hut has fewer than 100 parts total. Every component is simple enough to understand and repair in field conditions. Efficiency: maximum strength from minimum material. The arch shape does more structural work per pound of steel than any rectangular design. Every ounce of material serves a purpose. Manufacturability: designs mean nothing if you can't produce them at scale. The Quonset hut used standard industrial processes and equipment that American manufacturers already owned, allowing rapid production scale-up without building new factories. Adaptability: the basic structure accommodates countless modifications and uses. It's a blank canvas that users can adapt to specific needs without compromising core functionality. Resilience. The design forgives mistakes and survives abuse. Imperfect assembly still produces a functioning structure. Damage that would destroy other buildings becomes repairable in a Quonset. These aren't just engineering principles, they're design philosophy applicable far beyond buildings. The Quonset approach influences everything from disaster relief to space exploration because it represents a fundamentally sound way of solving problems under constraint. The story of the Quonset hut teaches lessons that extend beyond architecture and engineering. It's about how crisis drives innovation, how constraints force creativity, how the pressure of impossible deadlines can produce solutions that outlive the crisis that created them. The team that designed the Quonset hut didn't have time for perfection. They had 60 days to create something that worked. That time pressure forced decisions that turned out to be brilliant in hindsight, eliminating the floor, using self-supporting arches, prioritizing field assembly over factory perfection. Had they had more time, they might have over-engineered the solution or added features that made it more complex and expensive. The deadline stripped away everything non-essential, leaving only what mattered: shelter that works in the worst conditions imaginable. The success also came from empowering the right people. Otto Brandenburger wasn't a famous architect or an admiral. He was a structural engineer who designed farm buildings. But he understood the principles that mattered: strength-to-weight ratios, cost-effective manufacturing, field assembly by unskilled labor. The Navy was smart enough to give him authority and get out of his way. The willingness to iterate rapidly, build, test, fail, redesign, repeat, proved crucial. In 60 days, the team went through more design iterations than most building projects see in years. That rapid prototyping approach, now standard in Silicon Valley, was revolutionary in 1942. It worked because the team focused on solving problems rather than defending decisions. The feedback loops between field experience and design improvement created a learning organization that continuously refined the product. When Marines in Guadalcanal cut extra ventilation holes, engineers didn't get defensive about the design being modified. They incorporated the feedback into the next production run. That humility, accepting that field experience teaches lessons design can't predict, made the Quonset better with each iteration. By 1945, the United States had manufactured approximately 170,000 Quonset huts of various sizes and configurations. Total program cost: roughly $200 million in 1940s dollars, equivalent to about $3.5 billion today. For that investment, America got housing for 6 million military personnel across every combat theater, hospital facilities that treated hundreds of thousands of wounded, command centers that coordinated military operations, supply depots that stored and distributed war materials, workshop facilities that maintained equipment and weapons, communication centers that connected the global war effort, and after the war, emergency housing for 100,000 veteran families during the housing crisis, classroom space for 500,000 students in the baby boom, church buildings for thousands of congregations, commercial space for tens of thousands of small businesses, agricultural buildings on countless farms, industrial facilities for post-war manufacturing expansion. The return on investment dwarfs any conventional building program. The structures that cost $1,094 each in materials delivered decades of service across military and civilian applications. Some continue serving 83 years later, maintained by enthusiasts who recognize their historical significance. More importantly, the Quonset hut proved that radical design innovation can emerge from crisis. That constraints breed creativity rather than limiting it. That solutions designed for specific problems can find unexpected applications far beyond their original purpose. That simple, robust designs outlast complex, sophisticated ones when conditions get difficult. In 2018, researchers exploring Guadalcanal discovered the remains of several World War II-era Quonset huts still standing in the jungle, 76 years after their construction. The structures are corroded, overgrown, and partially collapsed. But they're recognizable. The characteristic arch shape persists. The corrugated panels, though rusted through in places, maintain their distinctive profile. Local residents had been using the abandoned huts as storage sheds and shelters for decades, unaware of their historical significance. To them, these were just old buildings the Americans left behind. Useful, but unremarkable. The researchers documented the sites, photographing the structures from every angle. The reports note that despite 76 years of tropical weathering, rain, humidity, salt air, vegetation growth, the basic structures remained intact. The roof lines held their curves. The panel connections still showed their bolt patterns. These buildings, designed for a 5-year wartime lifespan, had lasted 15 times longer than anyone expected. Similar discoveries happen regularly across the Pacific. Remote islands that saw brief American occupation during the war still host rusted Quonset huts that refuse to completely collapse. Antarctic explorers find abandoned research station huts from the 1950s and 60s still providing shelter from blizzards. The structures persist because their fundamental design works so well that even severe degradation doesn't destroy their basic functionality. In the depths of the Great Depression, American workers needed jobs. Steel mills needed orders. Engineers needed problems to solve. The Quonset hut provided all three: a wartime necessity that employed thousands, consumed millions of pounds of steel, and challenged engineers to rethink everything about how buildings work. In the desperate days after Pearl Harbor, the military needed shelter for millions of men deploying to fight across the Pacific. Traditional construction couldn't possibly meet the demand. The Quonset hut solved the impossible equation: fast, cheap, reliable shelter that could be manufactured at scale and shipped anywhere. In the chaotic aftermath of victory, veterans needed homes, and communities needed buildings. Post-war prosperity required infrastructure that conventional construction couldn't deliver fast enough. The Quonset hut, designed for war, found new purpose in peace: housing families, sheltering congregations, enabling commerce. Today, when hurricanes destroy communities, when earthquakes level cities, when refugees flee war zones, the same principles that drove Quonset development still apply. The arch geometry that deflects wind, the prefabricated components that ship efficiently, the simple assembly that doesn't require specialized skills, the robust design that survives conditions that destroy other structures. The Quonset hut isn't just a building, it's a demonstration of what happens when smart people face impossible problems with limited time and resources. It's proof that great design often comes from constraint rather than abundance. It's evidence that solutions created for specific crises can persist for generations beyond anyone's expectations. From the beaches of Guadalcanal to the suburbs of post-war America, from hurricane zones to refugee camps, from Antarctic research stations to proposed Mars habitats, the influence of 30 engineers working in a Rhode Island warehouse in 1942 continues to shape how humanity builds shelter under difficult conditions. The Quonset hut succeeded because it embraced what buildings actually need to do: protect people from weather and danger, and eliminated everything else. No aesthetic pretension, no architectural theory, no complexity for its own sake, just physics, materials, and the stubborn determination to make something that works. When Japanese artillery spotters watched those curved structures rise on Iwo Jima, they were witnessing more than American industrial capacity. They were seeing the future of disaster housing, the template for refugee shelters, and the blueprint for building on Mars. They just didn't know it yet. The machine gun cruiser earned her nickname through firepower. The Quonset hut earned its legacy through endurance. Both proved that sometimes the simplest solutions, rapid fire from well-designed guns, curved steel sheltering desperate men, win wars and outlast the crises that created them. In warehouses and farms, on military bases and in museums, thousands of Quonset huts still stand. Corroded, modified, adapted, but standing. They remain what they always were: proof that good design transcends its original purpose, that wartime necessity can produce peacetime abundance, and that 60 days of focused engineering can create solutions that last for generations. The steel has rusted. The paint has faded. The men who designed and built and lived in these structures are mostly gone now. But the principles persist. In every arched shelter, every prefab structure, every rapidly deployed building that saves lives in impossible conditions. They called it a Quonset hut, a name borrowed from a Rhode Island Navy base. But it was always more than that. It was American ingenuity made steel. Desperation transformed into innovation. An impossible deadline that produced an enduring legacy. In the curved walls of corrugated metal, in the simple geometry of a perfect arch, in the bolt-together panels that anyone can assemble, there lies the story of how engineers designed shelter to survive storms, bombs, and jungle heat. And in surviving all that, the Quonset hut did something nobody predicted. It survived peace, prosperity, and 8 decades of history. One hell of a building, one hell of a story.